record anything on here. Okay, can you guys see okay? Okay, so what we'll do on this is logarithmic differentiation. What I was trying to show you, we got into some pretty heavy problems last time. Logarithmic differentiation does make things a little simpler because you can use the log properties to simplify the expression. So the first thing we're going to do, when you do logarithmic differentiation, you want one side equal to y. And then what you're going to do is you're going to do the derivative of both sides. So you want to go ahead and start this like this. So we're going to take the derivative with respect to x of both sides of this equation. Okay, like that. So you always start that way. Now, when you do the derivative of y with respect to x, that's just dy dx. Technically, the derivative of y is 1, but since the variables don't match, then you do dy over dx like we learned when we're doing implicit differentiation. You don't have to think of it that way. It's just dy over dx, okay? Now, you got to think about the right rule. Now, you have to look at these problems the right way. When I look at this problem, I kind of look at this like I've got something to a power. Okay, that's what I'm differentiating, is something to a power. When you differentiate something to a power, what do you really do? I hate it when I press that button. Okay, you bring down the n, you leave the question mark, what's inside alone, you subtract from the exponent, then you take the derivative of question mark. Okay, that's a good way to look at it. Okay, so it's a generalized power rule. Okay, you got to look at it that way. All right. Now, you know what I did? I'm already starting wrong. I just realized I'm trying to teach you logarithmic differentiation. This is not how you start. My apologies. I'm not woke up yet. First, step one is to take the logarithm of both sides. Okay, I'm not paying attention to the directions. I'm just really going through and doing implicit differentiation. But let me just kind of erase that and let's start again here. So, sorry about that. It'll all work out the same way. So again, let's do this like this. We want to start by doing the logarithm of both sides. So we're going to do the natural logarithm of both sides. And if you started out the problem the way I was doing it, you would have got the same answer. It's just a different technique. Okay, so the reason we do this is because there is a basic property of logarithms. Remember, if you have a log of something, like a function, to a power, what are you allowed to do to the n? Bring it in front. Now, don't confuse that with taking a derivative. That's just a property of logarithms that you've learned. So let's bring this down. That's ln y. The sign of x comes down. I'm not doing a derivative. A lot of times students don't see that. I'm using a log property. Okay, so I'm doing that then. Okay, so what I've done is that. So now I can go through and I can do my derivative from this point then. So you got to start by doing that property like that. Now what we're going to do next is we're going to do the derivative using logarithmic differentiation now. Okay, so we're going to go ahead next and we're going to do the derivative of both sides. So we're going to do the derivative of ln y, because now we're doing implicit differentiation. Then we're going to do the derivative of sine x times ln of 1 plus x, like that. Okay, do this implicitly now. Okay, now what is the derivative of the ln of y? What did we learn last time? It's 1 over y, right? It's just 1 over the function. However, since the variables are not matching, what do you have to do? That's really a chain rule, so you have to write dy over dx. Okay, so that's kind of your implicit differentiation we've been working on. Now, if you look at what we're getting ready to differentiate, if you look at this, what have you got going on? What kind of rule is going to apply here? That's a product rule, because you've got two functions being multiplied. You've got a sine x and you've got an ln. So you're going to have to apply that product rule when you do this then, okay? So let's go ahead and do that then. So we're going to do the first, which is sine x. Don't do anything with it. Then we're going to multiply by the derivative with respect to x of ln of 1 plus x, like that, plus the second, which is ln of 1 plus x, and then multiply by the derivative of the first, like that. Okay, so that's product rule. You got a product of two functions. We've been doing that pretty consistently here for a while. Okay, so let's go ahead and write down the left side, just write it down as it is. We got 1 over y times dy over dx. We're going to do something with that kind of at the end of the problem. And then let's go ahead and let's finish up what we're doing here. So we're going to do this derivative, and we're going to do that derivative, kind of clean it up, and then we'll have an answer that we have done with logarithmic differentiation then, okay? Any question about anything so far? Okay, all right, so this is going to be sine x. All right, what is the derivative of ln of 1 plus x going to be? 1 over 1 plus x times the derivative of 1 plus x. Okay, that's a chain rule because that's the ln of something other than x. So you're going to go 1 over 1 plus x times the derivative of 1 plus x. You can do that in your head. What's the derivative of 1 plus x? That's 1, okay? It's 0 plus 1, right? So you can just do that in your head if you want to. Okay, pretend like that 7's not there. I don't want that to confuse you on the problem. Okay, so now we have plus ln of 1 plus x. What's the derivative of the sine? Cosine x. Okay, so we got that done. All right. Now I'm going to move this over here. Or actually, I'll just move down to the bottom here. I think I got room to do that. I'm not really done with the problem because dy over dx is not by itself. So how do I get dy over dx by itself? I multiply by y, right? Okay, and the reason I got to multiply by y is I got to get rid of that y. Okay, so I'm going to do that. That'll cancel out, and then you have to take this whole side here, and you got to multiply that by y. Now we're going to be ready to write the answer. There's one kind of important thing that you typically want to go through and do on these problems too, is this. So you end up with dy over dx like this. Okay, and that's really your derivative, but notice that we would really like everything to be in terms of x. So you go back and there's something that you do with y. You have to do something. What is y anyway in this problem? It's the original problem, right? So you replace it back. So that's the other thing. A lot of times that's an easy thing to forget to do. So you have to go back now and you replace y with 1 plus x sine x. Okay, and then on this you can clean this up a little bit. So you can put the sine x over 1. You could write that as sine x over 1 plus x, like that. And then this one, you can write it this way. It doesn't matter how you write this. I'm going to just write this as cosine x times ln of 1 plus x, and that should be a good answer to the problem right there. Okay? All right? Now let's do a second derivative, then a third. No, I'm just kidding. Okay? You can get in, like we've been talking about, is you can get in some pretty messy answers, but really that's not too bad. I mean, the product rule is not too bad. You didn't have any fractions to worry about and everything. And see, the fact that we could bring that sine x down after taking the logarithm really simplified it a little bit. Okay? And you don't have to do much simplification on this. That's a good form of that derivative like that. Okay? How's that look? Yeah.
How did you get the derivative of ln 1 plus x?
Okay, yeah, that's what we learned last time.
Yeah.
And the way you want to think of this is like this. First of all, if you do just the basic derivative of ln of x, that's 1 over x. That's the rule. Now, whenever you change that x to something, I'll put a question mark there. That's just something else. Okay, in this case, it's 1 plus x. What you do is you do 1 over that function, and then you multiply by the derivative of that function. So what I did is I did 1 over 1 plus x times the derivative of 1 plus x. So that's 1 over 1 plus x times 1. So that's where it came from. Okay, that's a chain rule for a natural logarithm. That's what I'm doing. Okay, so that's where that piece right there came right there. That's what I'm doing. Okay, does that make sense? Okay, right? Anything else you got a question on? Okay. All right, let's proceed and see what else we got here. Okay, so I'm going to look at these rules right here, kind of develop a couple more rules. Okay, so what we're going to look at is if you have a function of this type. Okay, now that would be like something like 2 to the x, 10 to the x, or whatever. Okay, a is just some sort of a constant, even if it was square root of 2 to the x. Okay, we can do the derivative of that. Now, a lot of times students have this idea that I should just have to do this. Just bring that down, do that. Unfortunately, it doesn't work that way. Okay. That only works, in this case, you're kind of getting this confused with if you have x to a power. Well, if you have x to a power, yeah, you bring that down, and the power rule that we've been doing. Now, this is not a power rule, so don't get that confused. So the derivative is this, and I'm going to go ahead and I'm going to show you where that comes from. Actually, the proof of that's really easy to do. You can use logarithmic differentiation to show that in case you forget that, okay? So what it is, if you're doing the derivative of some constant to the x, it's just itself times ln of a. Now, that itself issue kind of comes like this. If you think of this, we already know that the derivative of e to the x is what? Itself. So it's kind of the same here. It's itself, but then you have to multiply by that logarithm of a. That has something to do with change of base and that kind of idea like this. So let me show you how you prove this. Let's just start by writing down y equals a to the x like this. And if we do this, I think the other way you could probably do this is you can do logarithmic differentiation, but you can also use the change of base formula on this. So let's just start it like that. Logarithmic differentiation, what we do is we take the logarithm of both sides. That's step one. Okay, step two is to take the derivative with respect to x of both sides of this equation. Hold on, I always forget this, okay? What do I need to do with that x? I need to be paying attention, okay? Because if I don't do that, it's going to mess me up here, sorry. Okay, so we have a property of logarithm that says you can write this as ln y equals x times ln a, okay? That's a log property, it's not a derivative. Now what we're going to do is we're going to do the derivative of both sides of this equation. Okay, so we're going to do this and just kind of think about how this would work out, okay? And one of the reasons I like to go over the proofs of these things is because there's a ton of rules to remember in calculus, and being able to derive stuff is very helpful when you forget things, okay? It's a good thing to know. It also gives you a sense of where everything comes from. All right, so what is the derivative of ln y? There you go. 1 over y times dy over dx. That's a chain rule. The variables don't match. Now, when you do this derivative here, you may be thinking product rule, which would work, but it's not necessary. ln of a is a constant, so it comes out of the derivative, so you can just write this as ln of a times this. Yeah, like that then. Okay, so we're just going to have ln of a times the derivative of x, like that. Okay, that's a constant. All right, so this is going to be 1 over y times dy over dx. This is going to be ln of a, and then what's the derivative, of course, of x? It's just 1. You don't have to put the 1 there, but that's what you're technically doing. Now, I'm not done with the problem. I got to solve this equation for dy over dx, so what do I have to do? Now, I got to multiply both sides by y, so I'm going to multiply this side by y, this side by y. That's going to now leave me with dy over dx is equal to ln of a. Okay, so that ln of a is there. Okay, now what do you have to do with y? You got to substitute in what y is. So y is really a to the x. Okay, then you proved the formula. Okay, so that's what we just did. It's a to the x times ln of a. That's it. Okay, so logarithmic differentiation, it comes in handy for all kinds of things. A lot of times when we get these different techniques, it leads to other discoveries and stuff. So we use that to prove other things then. Right? So if we have a chain rule, the chain rule, all the chain rule's ever saying is instead of having like a to the x, you have a to something. That's a function. So what do? Just think of that as when you do the derivative of a to the f of x, where a is a constant, first of all, it's itself. Okay, it's just itself. Okay, just like it is on a e to the x. Okay, then you still put the ln of a. Then you got to do the derivative of that exponent like that. Okay, a lot of times when you learn these chain rules, it's good to learn it kind of in words. Really, it's the same. It's itself times ln of a. The new thing is you multiply by the derivative of that function. Okay, that's what you always do in the chain rule. Okay, so that's kind of how that goes. Now, I do want to show you guys just one other thing on here while I'm thinking of it. Okay, if we were going to do the derivative of e to the x using this formula, now you already know that the derivative of e to the x is e to the x. Okay, I'm not giving you a new way to learn this. Okay, but if we use this rule, you know what we would do? According to this rule, it would be itself times the natural logarithm of the base. Do you guys know what ln of e is? It's 1. So look at this. Okay, you end up getting e to the x times 1, so it's equal to e to the x. E to the x is very special. I mean, it's a special case of this derivative rule, and just because ln of e is 1, that's why it ends up being itself. Any other situation, you have that ln of a in there. Does that make any sense? Okay, so e to the x comes from that formula. It really does. You can look at it that way. Okay, so these derivatives are pretty easy to do. I'm going to do a couple of examples on this, and then we're going to look at one more derivative rule that I want to teach you. So we're just going to follow the basic formula on this. Okay, so the formula I'll kind of highlight up there so we can kind of refer to this as we're going. Okay, and these are not going to be chain rules on this example. And we're going to do 3 derivatives because it's fairly easy to do on this. Okay, so 2 is a constant. So the answer to this problem is itself, and then what? ln of 2. Problem done. That's it. Okay, all right. Now if we do the second derivative of this, we're going to take the derivative of this, of course. Now, don't do product rule. If you did product rule, it'll work, but ln of 2 is a constant, isn't it? So it's not a part of your derivative. So when you do this, you're really going to do, just take the ln of 2, then you're going to multiply by the derivative of 2 to the x again. Okay? Remember, if you have a constant times a function, you just write the constant down and multiply it by the derivative. That's one of the basic derivative rules we learned. Okay? All right, well, so what you're going to do is write down the ln2 again. Now, didn't we already do the ln of 2x? Okay, we just do it again. So it's going to be itself, 2 to the x, times the logarithm of 2. Okay, so what you're going to end up getting is you could write the ln of 2 as the ln of 2 squared, because it's just that by itself. Okay. Don't you dare put ln of 4, though. I see students do that all the time. You don't just square the 2. It's the whole thing that's squared. Okay? Then you're going to take times 2 to the x like that. Okay? And you'll kind of see a nice pattern on this one. Okay? What do you predict the third derivative is going to be?
ln of 2 to the third times 2 to the x.
Yeah. Okay, so it's going to go to another power. Exactly. Okay? So when we do the derivative of this, again, what you're doing is the ln of 2 to the second is a constant, so that's not a part of the derivative. Then you just do the derivative of 2 to the x, and you do it again. Okay, all right? Don't use a product rule. It's not necessary. So you're going to have ln of 2 to the second. That's the constant. And then again, what's the derivative of 2 to the x? Itself times derivative times ln of 2. Okay, like that. So again, itself, 2 to the x, times ln of 2. So yeah, that answer is going to be, you now have 3 factors of that. So you'd have ln to the second, ln of 2 to the third, times 2 to the x. So that would be your 3 derivatives right there. Okay, that's pretty simple to do. I like that problem just because it shows a pattern. Okay? All right, does that make sense? Okay? Now, once you catch on to this rule, it's very easy. Of course, it's another thing to remember. But just as an example, what if you had 11 to the x? If I want you to do the derivative of 11 to the x, what's the answer? Itself times ln 11. Like that, okay? It's just like the exponential, except you have that logarithm of the base. That's the only difference, okay? The derivative of e to the x is a special case. All right, any questions on that? Okay, all right. Now let's go do this next one. This next one's real simple. You can do this one in your head, okay? So this one right here, you're doing an ln on. So again, you got to look at these problems the right way. So when you're doing the derivative dy over dx on this, what are you really doing? You're doing, the structure is the ln of a function, right? You're differentiating an ln. 10 to the x is just a component of it. So how do you do the derivative of ln of something? In words, how do you do that? 1 over the function times the derivative of the function. Okay, that's the chain rule for logarithms. So what we're going to say, see, the function is that argument. That's changed. That's not ln of x, it's ln of 10 to the x. So by the chain rule, we say 1 over 10 to the x, then we have to multiply by the derivative of 10 to the x. Okay, that's what we were working on last time in class, is that. Okay, so now we got one more thing to do, essentially. So the 1 over 10 to the x comes down, okay? And when you do this second derivative, this is what we've been working on. What is the derivative going to be of 10 to the x? 10 to the x times ln of 10. Good, okay? So that's the rule that we're working on right now. So that derivative is going to be itself times ln of 10. So is the problem done? There's a simple cancellation, isn't there? Okay, you can reduce that. That's 1. So the answer is ln of 10. Okay, whatever that is, that's a constant. That's the exact answer. If you did that on your calculator, ln of 10, you'd get a bunch of decimals and stuff. Okay, right? Does that make sense? Okay, we got chain rule embedded from here on out on most of these derivatives. So chain rule's huge as you're doing most of these problems. Okay, let's see what we got on this one then. So we're going to do g prime of t. Well, again, you got to look at it the right way. Students a lot of times have a tendency to look at the problem the wrong way, and they're thinking, I need to start by taking the derivative of 3 to the 10th. No. The structure of this problem is you're doing the derivative of a cosine of something. So what's the derivative of the cosine?
Negative sign.
Negative sine of the something. Then what? Times the derivative of the something. See, that's what chain rule is. It's the basic rule times the derivative of whatever that change is, what that function is. So when you do this, you're going to do this exactly like this. You're going to say it's negative sine of that something times, then we're going to do a derivative with respect to t. So I'm going to write that as d dt of 3 to the t, of that function like that. Okay? So now we're going to have negative sine of 3 to the t. Okay, this is what we just learned. So what's the derivative of 3 to the t?
Itself times
Oh, wonderful. You even said that in words. Itself times ln of the base. Okay, if you learn it that way, it'll help you make sense of that. Itself times ln of the base. Okay, and that's a good answer. It doesn't matter what order you write that in. I think I like it better for whatever reason if I write the 3 to the t in front, negative 3 to the t, then maybe the ln of 3. It doesn't matter. I think it's probably best to kind of write it something kind of like this. I mean, it doesn't really matter, but the idea is you want to make sure that you understand that the sine and the ln are totally different things. Okay, like that. So it doesn't matter what order you have that in, so that's the idea. Okay, does that make sense? Okay. Chain rule. It takes a while to get that chain rule under control, but that's huge. Okay, it's going to apply, like I said, to the vast majority of the derivatives that we do. Okay.
Can you get that over here? There's one more second.
Okay. Yeah, no problem. All right. Any questions? I want to just look at a few other things. I am going to go ahead and teach you one more rule. There's one more derivative rule on here. We'll take a look at that. Everybody got this copied down now? Okay. All right. Okay, so on this next one, I'm going to go through this derivative rule. Now, this is looking at the derivative not of ln, but just any other logarithm. Okay, so we're going to prove this rule. This is a real easy rule to derive. So it turns out if you're doing the derivative of log base a of x, it's 1 over x times ln of a. Well, the 1 over x that's what you're familiar with, right? The derivative of ln x is just 1 over x. Every other base is a different case. E is very special. It's a very, very special number in calculus. So what we're going to do on this is I want you to start by writing down what we're differentiating. So we're going to develop the derivative rule for log base a of x. Okay? Now, there's something called the change of base formula. I'm sure you've learned about that in college algebra. I put that on the beginning of your notes on this, but the change of base formula goes like this. We're going to change this to an ln of the argument x and divide by the ln of a. Change of base formula goes like this. So one of the things you probably did in college algebra, for example, is if you had log base 2 of 7. You can't do that on your calculator because you don't have a base 2 log button, but you can put it in your calculator this way. You can go ln 7 over ln 2, and that works. Okay, that's why you only have 2 buttons on your calculator for logarithms, because you only need 2. Really, you only need 1, and that's the ln. Okay, ln's the big important logarithm. It's the special one. Now, we're going to write this as 1 over ln of a times ln of x, and then we're going to do the derivative of that. So what we're going to do next is we're going to do the derivative of 1 over ln a times ln of x. And when you do that, the rule is there for you. Okay? What kind of number is 1 over ln a? Constant, right? A is a constant. A is just a number. It's not a variable. A is a constant. So remember, you don't have to use product rule. That's a constant, so pull it out. So you're going to have 1 over ln a times the derivative of ln x. What's the derivative of ln x? 1 over x. So notice what you have is 1 over ln a times 1 over x. Well, that gives you that. That's it. That doesn't matter what order you put it in. You can multiply the fraction straight across, so you would get that like that. So that's the basic rule. Okay? So the only difference on that is the 1 over x, but then you have the ln a also because you have a change of base from the base e. Now, if you do a chain rule, the chain rule works out like this. Okay? You're just looking at log base a of something other than x, a function. So think about what you do. What do? You do exactly what you do over here. Instead of saying 1 over x, you say 1 over f of x. You still say ln of a. But the chain rule always has this component. You multiply by the derivative of what's different. It's always the same. Okay, does that make sense? Always multiply by the derivative of whatever that function is that makes the problem different. Okay, because it's a composition of functions. Okay, so let's look at a couple of problems. Now, one thing that I teach students to do on this is if you forget the rule, and if you just use the change of base formula, you can always work it out that way. So I'm going to do this problem 2 ways. I think it's good to know how to do this 2 ways. So if we do the derivative of log base 10 of x, I'll scroll this down because we want to look at this rule. So it's just direct application of this rule right here. You're just applying the rule that we just proved. And it goes like this, okay? It's going to be 1 over x, whatever that is, times ln of 10. Problem done, okay? Now, I do want to just show you something right now, too, because this is also kind of important to see. If we did if we did the derivative of ln x using this rule, let me show you what would happen. According to this rule, this would be 1 over x times the ln of e, right? Just like this is 1 over x ln of 10, this would be 1 over x ln of e. But what is ln of e? It's 1. See, it's special. E is special. It's a special case for logarithms. Okay, so that's how it works out. Now, let me show you another way to do this. So I'd like you guys to know how to do this also. I do this all the time. A lot of times I forget the rule, although it's easy to derive. I just look at that, and someone asked me how to do a derivative on that, and I've forgotten. Here's what I'm going to do. I'm going to use the change of base formula, and I'm just going to write it like this. Okay, that's what the change of base formula says, is that would be ln x over ln 10. Now, if I want to do the derivative of this, I'm really looking at this as 1 over ln 10 times ln of x. I write it that way because isn't 1 over ln 10 just a constant? Okay, so it can come out of the derivative. So that would be 1 over ln 10 times the derivative of ln x. But what is the derivative of ln x? It's 1 over x. So you have 1 over ln 10 times 1 over x. Well, that's going to give you the same thing anyway. I like to show that because I do that all the time. I forget that rule. You have so many derivative rules, it's easy for people to forget these things. So you want to have strategies of being able to come up with these. Does that make sense? Okay, to me, it's just as easy to do the problem that way. Okay, helps me make sense of how that rule works anyway. So you can do it either way. Okay. Okay, so let's look at it. These next two examples are doing chain rules. So one of the things that you want to do on the chain rule on this is when you're doing the chain rule on a derivative of a logarithm other than e, base e, you're really just doing 1 over the function times ln of whatever that base is times the derivative of the function. Like that. That's really what you do when you're doing chain rule on this. Okay. So when you're doing this one, this one's going to have a couple of chain rules in it. So the idea is log base 2, you're doing a log of a log, which you can do. You can do a log of a log of a log of a log infinite times if you wanted to. Okay. It can be done. So what we do on this is you're applying this structure. So when we do this derivative, it's going to be 1 over the function. Okay, and that's what you're taking the log of. So you're going to do that. It's 1 over the function, which is log base 2 of x, times ln of a, which is that base. Then you're going to multiply by the derivative of that function, log base 2 of x. Okay, so that's again what you're doing. When you're taking the derivative of a log of something, it's 1 over that something times ln of the base times the derivative of that something. Does that make sense? That's chain rule again. You got that times the derivative. Okay, now let's see what we got here. So this is 1 over log base 2 of x times ln of 2. Now let's focus on this derivative. This is really what we just learned as we did that rule right there. So if you got the rule down, you could tell me what that derivative is in your head. What is the derivative of log base 2 of x? 1 over x times ln 2. Good. Okay, so that should be a time sign. So again, we'll say 1 over x times ln of 2, like that. Okay, so that's how that gets put together. Okay, now what we're going to do is multiply this straight across. So we have 1. Notice on here that you have an ln 2 times ln 2. Again, don't put ln 4. How you write that? ln 2 to the second. That's it. Just write it that way. Okay. Then you can write the x. Then you can write log base 2 of x. It doesn't really matter what order you write it in, but to me that's a preferred way to write that because you want to have just the log of x by itself so that you understand that you're just doing log of x. You're not doing log of anything else. So that's your answer. Okay? All right. Does that look okay? Okay. That's all when you learn these derivatives. You have to look at that first step the correct way and know what rule applies to it. And then generally chain rules going on most of the time. Okay? All right, so let's see on this one. Now, we do have a square root, so let's go ahead and do what we're used to doing with square roots. Let's write this as x plus 1 to the 1/2 power like that. Then let's go ahead and do the derivative. Okay, so when you're doing this derivative, you're going to do exactly what this chain rule over here is telling you to do. You're going to do 1 over this function. Now that function's a fraction, so what? Just do 1 over that function times ln of 5. Okay, that's the general thing that you do on this is 1 over the function, but then you have ln of 5. Then what else do you got to do? You got to multiply by the derivative of that function, 8 over x plus 1 to the 1/2 like that. So we got to focus on that. So that is the setup for that derivative in a chain rule. Okay, a couple of things on here that you can do. Now, when you're looking at this, you're really dividing. You're really doing 1 divided by, and let's forget about the ln 5, 8 over x plus 1 to the 1/2. Okay, how do you divide fractions? You flip. Okay, so this is really, if you think about this, okay, when you flip that and multiply that, you're going to have x plus 1 to the 1/2 over 8, right? Okay, and that ln 5 is just going to stay where it is. It's in the bottom. Okay, like that. Okay, so you can do that in your head if you want to. You can learn to do that in your head. You're doing 1 divided by a fraction, so it's 1 times the reciprocal, right? Okay. Now, when we do this derivative, you could do the quotient rule, but you don't have to, because what kind of number is 8 anyway? It's a constant. So you can bring that constant out, and then you can multiply that by the derivative of this. Now, that really would be 1 over x plus 1 to the 1/2. You don't have to use the quotient rule. What can you do to that x plus 1 to the 1/2? You move it to the top, making the exponent negative, and then you can use a chain rule. To me, it's easier. So I'm going to move this to x plus 1 to the negative 1/2. If you do the quotient rule, it'll work beautifully. It's just harder. It's just more work. Okay? So you can do it like that. Now, when we put this together, we're going to have x plus 1 to the 1/2 over 8 ln 5 times 8. Those 8's are going to cross out. Now we're going to do this derivative right here, which is just a basic kind of extended power rule, if you want to think of it that way. So it's negative 1/2 x plus 1, subtract 1 from the exponent, and then technically you don't have to write this because you're doing this in your head. You're doing the derivative of what's inside because you're applying a chain rule, like that. So what you're going to have then is the 8's are going to cross out. We're going to have x plus 1 to the 1/2 over ln 5 now, times negative 1/2 x plus 1 to the negative, and that is, why did I do a negative 2/3 there? I think I meant to say negative 2 over 2, so that's negative 3/2. And of course that derivative right there is 1, like that. So that's your derivative, and you just clean it up a little bit. What I would suggest we do for simplifying this, we do have a negative answer. So I have a negative somewhere. I'm just going to make this in one fraction. So I'm going to leave the x plus 1 to the 1/2 where it is. I'm going to move this thing to the bottom because it has a negative exponent. So it's going to be x plus 1 to the 3/2. Now let's see. Those are taken care of. We have a 2 and an ln 5 there in the denominator. So let's just kind of squeeze that in like that. Okay. Now you could do a simple thing with these like terms right there. Couldn't you just subtract the exponents? Because they're the same. Yeah.
What happens to the 8?
What's that? It canceled out right here.
Oh,
Okay. So those cancel out. Okay. All right. So we could go through and do this. We have a negative here, and then we have x plus 1 to the 1/2 minus 3/2, and it's still all over 2 ln 5. I'm just saying, hey, you can subtract those exponents. It's no different than having x squared over x to the 3rd, which is x to the negative 1. So this is going to end up being like this. You would have negative x plus 1 to the negative 2/2, which is kind of cool, over 2 ln 5. So this is negative x plus 1 to the negative 1 over 2 ln 5. And then what else could you do? We got a negative exponent, so why don't we move that down to the bottom? Okay, so that's a negative 1 power. So probably the best way to write this answer is negative 1 over 2 ln 5 times x plus 1. Okay, I took that one all the way to the end. Okay, students oftentimes struggle with radicals because there's so much going on with fraction arithmetic and stuff like that. Okay, that's a pretty messy one. How's that look? Most of what I did is algebraic rules with exponents. The vast majority of what I did is that. Okay? All right, so I'll go ahead and end that up here, and then we're going to go ahead and start.